Hello, I'm Yongbong Kim from Dongguk University, DTM Lab. Today I'm going to review a paper titled International Comparative Research on the Relevance of Science and Technology and the Innovation Ability of the Rare Earth Industry from the Perspective of Technology Industry Mapping based on patent information. This slide shows the bibliographic information of the paper. This paper is published in Resources Policy in 2023 and it focuses on the rare earth industry from a patent-based perspective. The authors propose a technology industry mapping framework using large-scale patent data to analyze global innovation patterns in the rare earth sector. By applying science, technology, and technology-technology correlation indices such as TSIC and TTCI, the study compares how different countries innovate across upstream and downstream stages of the value chain. Overall, the paper aims to reveal systematic differences in innovation structure and capability among major rare earth countries. Here are the contents of today's review. First, the authors explain the research background. Rare earth elements are regarded as strategic resources that are essential for high-tech energy, aerospace, and defense industries. Since the 1990s, China has dominated the global rare earth supply, accounting for nearly 90% of world production. However, despite this strong research dominance, innovation outcomes remain uneven, especially in downstream and high value-added applications. As a result, innovation-driven development has become a core policy objective for the rare earth industry, with an emphasis on high-end applications and reduced reliance on raw material exports. Recent global trade frictions have further highlighted structural weaknesses in downstream innovation. The authors also point out that existing studies mainly focus on patent quantity or technology trends, while the linkage between technology and industry has not been sufficiently analyzed. Next, the research purpose is introduced. The main objective of this study is to systematically map the relationship between technology and industry in the rare earth sector using patent data. The authors aim to analyze innovation characteristics across countries by distinguishing science-driven and technology-driven innovation patterns. In addition, the study compares national innovation capabilities along the rare earth value chain and seeks to provide policy-relevant insights for improving innovation performance and promoting industrial upgrading. Previous studies on the rare earth industry have expanded rapidly since the mid to late 1990s, mainly focusing on industry development, competitiveness, and policy issues, particularly in the context of China. Many studies evaluate China's competitiveness using indicator-based methods and strategic frameworks such as SWOT and Porter's diamond. Another major research stream addresses resource and environmental issues, highlighting problems such as resource waste, environmental damage, and difficulties in transforming resource advantages into market advantages. From a strategic perspective, rare earths are increasingly regarded as critical resources related to national security and global supply risks. In addition, technology-specific studies focus on applications such as magnetic luminescence and functional materials. However, most existing studies remain sector-specific or policy-oriented, with limited cross-country analysis along the entire rare earth value chain. This gap motivates the current study, which adopts a patent-based technology industry mapping approach. Advances in NLP attention mechanisms and text embedding based concordance methods further support finer grained analysis of technology market linkages. This slide summarizes prior studies that use patents as a proxy for innovation dynamics. Patents are widely used to analyze innovation activities, technological change, and competitive positions across industries and countries. Many studies use patent statistics to compare innovation intensity and technological advantages across industrial sectors, and other nations. In particular, patent citation analysis has been applied to examine the linkage between scientific research and technological innovation, distinguishing science-based industries from technology-based ones. In addition, patent citation networks are used to trace knowledge diffusion and technological evolution paths, enabling cross-country comparisons of innovation capabilities. In the content of rare earths, however, most patent-based studies focus on specific technologies or particular industry segments. As a result, few studies integrate patent-based technology industry mapping with cross-country analysis of innovation characteristics along the entire rare earth value chain. This gap motivates the approach adopted in this paper. This slide explains the data used in this study. The authors used the Derwent Patent Database as the main data source for analyzing rare earth-related innovations. Patents are retrieved using keyword-based search queries applied to titles, abstracts, and claims. Using this strategy, more than 81,000 patent applications are initially collected. After consolidating patent families to remove duplicates, the final dataset consists of about 42,900 unique patent records. The data were retrieved in July 2019, and patents published after 2018 are treated as reference only due to the time lag in patent publication. This slide explains the overall research method and analytical framework of the paper. As shown in the figure, the framework consists of two main analytical stages. First, the authors build a technology industry linkage structure by mapping patent data to both industries and technologies. Since technology classifications cannot be directly translated into industry categories, a concordance-based mapping approach is required. In this study, patents are linked to industries using an IPC and NASA Beaver's second concordance table. After this step, each patent can be clearly positioned within the rare earth value chain. This industry classification system is regularly updated with patent data and is highly comparable to China's national industry classification, which makes cross-country analysis more consistent. In the second stage, the study measures science, technology relevance, and innovation capability. Using these indicators, national innovation patterns are compared to distinguish science-driven and technology-driven structures in the rare earth industry. Overall, this framework integrates patent data, industry structure, and innovation indicators into a single analytical pipeline. This slide explains how the authors cluster technologies and measure scientific relevance. First, the rare earth technology chain is divided into upstream, midstream, and downstream segments. To represent technological fields, the study used DWPI technical codes from the Derwent database. Based on these codes, the authors apply a social network analysis approach to identify technology communities. In simple terms, technologies that frequently appear together in patents are grouped into the same cluster. Community detection is performed using a modularity measure called the Q value. When the Q value falls between 0.3 and 0.7, the clustering results is considered statistically meaningful, and the study certifies that condition. Next, the study measures scientific relevance using non-patent literature citations in patents. These citations indicate how closely technological innovation is linked to scientific research. To quantify this relationship, the authors use the Technology Science Correlation Index, or TSCI. A positive TSCI value indicates science-driven innovation, while a negative value indicates technology-driven innovation. Through this process, the study is able to distinguish whether innovation in each technology field is mainly driven by basic research or by technological accumulation. Technological relevance is measured based on patent citation frequency. Patent citations reflects how knowledge is diffused and how technologies are inherited over time. Using this idea, the study introduces the Technology Correlation Index or TTCI. TTCI is calculated as the ratio of cited patents to total patents in each technology field. The index is normalized from -100 to +100, which makes cross-country comparison possible. A higher CTCI value indicates stronger technological continuity and higher patent value. Innovation capability is then evaluated using patent-based indicators. The study adopts the patent strength share or TSS to measure technological innovation performance. TSS combines patent quantity, technological breadth, and citation impact, while the relative growth rate is used to capture technological development trends across countries. This is the results of the paper. Global rare earth patent activity shows two major peaks in the mid-1990s and around 2009 to 2010. The first peak reflects breakthroughs in mining and smelting technologies, while the second is linked to global trade expansion and policy-driven market changes. China accounts for the largest share of patents, followed by the US, Japan, and South Korea. These four countries together dominate almost all rare earth patent activity. Looking at the figure, patents are clustered into 10 technology fields along the value chain. China shows a clear quantitative advantage in upstream and midstream areas such as smelting, alloys, and oxides. In contrast, downstream fields like semiconductors, catalysts, and optics show stronger competition across countries with no single country dominating. This part presents the patent industry mapping and technology industry relevance. First, the patent industry mapping shows that rare earth-related patents are highly concentrated in basic chemical production. In addition, industries such as electronics, glass, ceramics, and basic metals are major recipients of rare earth technologies. China's advantages are mainly concentrated in midstream and equipment-related industries. In contrast, downstream application industries show weaker and less distinctive advantages for China compared to other countries. Looking at the figure on the right, the technology industry relevance network illustrates how different technologies are linked to specific industries. Most our Earth's innovations are rooted in basic material production, especially chemical and metal industries. Upstream technologies such as catalyst and metal or alloy technologies are strongly connected to these basic industries. Meanwhile, downstream technologies like semiconductors, optics, and modification technologies are primarily driven by application industries. Overall, the figure shows that innovation typically originates upstream and then diffuses into downstream applications, but the strength of these linkages varies significantly across technological fields. This is the results of scientific and technological relevance. The left figure presents the TSCI results. The US shows mostly positive values across the value chain, indicating science-driven innovation. Japan and South Korea display more technology-driven patterns supported by strong downstream enterprises. China shows relatively higher scientific relevance in upstream and midstream technologies. The right figure shows the TTCI results. The US and Japan exhibit higher patent value and continuity, suggesting stable technological inheritance. In contrast, China shows relatively weaker continuity, indicating lower technological accumulation over time. Overall, these results reveal clear differences in national innovation structures within the rare earth industry. Now the discussion focuses on the key implications of the results. Innovation in the rare earth industry has become a strategic priority for China, especially after WTO disputes and recent trade frictions. However, despite strong resource dominance, innovation efficiency remains relatively low, particularly in downstream applications. By constructing a patent-based technology industry correlation system and combining TSCI, TTCI, and TSS indicators, the analysis shows that industries differ in whether they are science-driven or technology-driven, and technologies are influenced by multiple industries to varying degrees. Overall, the results provide insights into where basic research is most effective, where applied research dominates, and how countries build innovation advantages along the rare earth value chain. The conclusions can be summarized into two main points. First, scientific research plays a critical role in supporting China leadership in upstream and midstream rare earth technologies. Strong basic research underpins original innovation in areas such as melting, alloys, and oxides. However, downstream application technologies, including semiconductors and optics, remain relatively weak, and improving research quality and international impact is still a key challenge. Second, while China has successfully integrated university and research institutes in upstream innovation, industry-led innovation in midstream and downstream sectors is limited. International cases suggests that downstream competitiveness depends heavily on strong enterprise participation and close links between materials research and application industries. Extending the production, education, research integration toward downstream sectors is therefore essential for upgrading China's position in the rare earth value chain. The remaining conclusions focus on enterprises, terminal technologies, and future research. Enterprises play a critical role in innovation capability. The US and Japan maintain strong competitiveness through leading downstream enterprises, while in China, high-value patents are still concentrated in universities and research institutes. This weak enterprise-led R&D results in low patent continuity and fragmented technological development, highlighting the need to cultivate strong leading firms in rare earth applications. Terminal technologies ultimately determine strategic competitiveness. Most value creation in the rare earth industry occurs in downstream applications, and the value distribution is heavily skewed toward terminal products. China remains vulnerable due to its reliance on foreign downstream technologies, making the development of terminal and application technologies essential for reducing external de- dependence and upgrading its strategic position. Finally, there are limitations related to patent quality differences and citation-based indicators. Future research should improve patent value rating and citation measures to enable more accurate assessment of innovation capability and science-technology linkages. Thank you for listening my paper review.